Today we're going to talk about LeetCode question number 104, maximum depth of binary tree. So given the root of a binary tree, return its maximum depth. Binary tree's maximum depth is the number of nodes on the longest path from the root node down to the farthest leaf node. Okay, so for example, this here, we always have to start from the root as the problem states, and then we have to find the longest path, counting the number of nodes on this whole path to the farthest leaf node. So for example, this is the farthest leaf node, or this is the farthest leaf node, it doesn't matter. The path length will be 3 anyway. 1, 2, 3. Okay, so simple. This problem description is simple enough. So how do we go about doing this? Well, one way is breadth first search. It's where basically we traverse the tree level by level, and as we do that, we pretty much count how many levels we're traversing. Okay, so the first level is where the root is, and the very last level is where the farthest leaf nodes would be. Okay, and in this case it would be 1, 2, 3. Second way would be breadth first search, or sorry, depth first search. Is where recursively we travel down each node's children, okay, and then travel through this guy's children over here, okay, and then along the way, while we do that, we increment a counter every time we go down by 1, okay. So for example, if we were traversing this path here, so we start here. Right now our counter is 0, and then we go down here, okay, we traverse down here, and then counter is 1, okay, and then since this is recursive, we have to reach a base case, and our base case in this case is if it's none, okay. So then we have counter equals 1 here, then we traverse down, now counter equals 2, but it turns out we're at our base case. Okay, so we return counter is 2, and similarly for here, counter would be 2, and then since we hit our base case, we return counter. Okay, and since our counter is 2, this is an accurate reflection of the number of nodes along this path. Okay, so this is 1, 2. Okay, so let's look at another example. Let's say we have another node here. Okay, and this is like 6 or something, or maybe 6, yeah. Okay, what if we have another node here? How will we traverse this tree? And by the way, when we're traversing the left and the right, we want to return the max, the left and right. Okay, so how will we go about this? So starting from here, our counter is 0. Okay, and then we go down here, counter is 1, and now we have 2 paths to take, so we'll take both paths. Here, counter equals 2, and this is none, and this has none, has children, okay, and we go to here, and counter equals 2, and then we go down here, equals 3, C equals 3, okay? And now what about traversing this tree? So we traverse down here, C equals, counter is 3, and since this is none, if we hit down here, C equals, oh sorry, 2, C equals 3, and we hit our base case, so we stop here. So for this path, 327, the number of nodes along that length is 3. But 7 also has a left child here, so we have to explore that. C equals 4, okay, and sorry, C equals 3, 2, 3, and then we go to its children, C equals 4, C equals 4, okay, and we hit our base cases, so now we're going to return C equals 4, but look, counter at 7's left child is 4, and counter at 7's right child is 3. So what we're going to do is return 4 since it's bigger. Okay. Then once we return that, it'll propagate up. Okay, and then we get our final answer of C equals 4. Okay, and that's how we're going to do with depth first search. The runtime is O of n because we only look at each node once, and time complexity would be also O of, I guess, O of h would, or h would be the height of the tree, because for recursion we have to store things in a stack here. Okay, now to code this up. So what we want to do first is check for an edge case where root is none. So if root is none, then obviously the length of our longest path is 0. Return 0. Okay. Now we're going to define our helper recursive function. And this base case will be if root none, return 0. Okay, why return 0? This will make sense in a second. So what I want to do is for every node, traverse the left subtree and the right subtree. So left is equal to helper root dot left plus 1. Okay, plus 1. Because we're incrementing every time we visit a new node here. We increment every time we're gonna visit a new node, and then right is equal to helper root dot right plus 1, and then we're gonna return the maximum of left right. Okay. And so why do we return 0 in the base case? So if you look, so for at root 3 over here, and we're doing root dot left. So we do root dot left plus 1. Okay, root dot left. Now counter is 1. Okay, and then what you want to do is again root dot left. So left, and then as we do that, counter becomes 2. Okay, so 1, 2, 2 nodes in this path. Okay, and now we recursively go through this again, and then it turns out over here, while our counter is 2, we're at a none. Okay, so once this is none, return 0, and we return 0, we propagate up the stack. So then we go 0 plus 1, and then when we pop back up here, it'll be 0 plus 1, return 0, okay, plus 1 at this 9 here, and then propagate back up. So then since we return the max of left or right, let's say it's 1 in this case, we return 1, 1 is the max, it'll be 1 plus 1, and then 2. Okay, so that's how recursion kind of works. And finally, what I want to do is call the method. Okay, let's test it out. Okay. I'll use other test cases. Okay, now I'll submit it. Okay, great. Thanks for watching.